Okay, can you hear me? And no feedback? Can you hear me? All right. Thanks. Okay. Okay, let me start recording. Okay, so let me start the second part of this course. It starts with integral calculus, but integral calculus will be mainly addressed to understand the basic models that are useful for dynamic analysis. Okay, so I will focus a little bit on indefinite integrals, which is point A here, section A. So the reverse of differentiation, finding the primitives of a given function. Then I will focus on the definite integral, which is apparently very different kind of problems, a method for calculating areas. But of course, there is a fundamental theorem, which is called fundamental theorem of calculus, that sets a bridge between A and B. Okay, so two very different problems have a strong connection. Okay, and this is established by this fundamental theorem of calculus. Understanding the fundamental theorem of calculus means also understanding a way to express dynamic phenomena, dynamic aggregates of dynamic flows by means of integrals. Okay, so it's not just important conceptually; it is also important in terms of notation. Okay, because you have to understand very well what the notation means of an integral that starts at 0, for instance, and ends at time t, where t is a variable time, of some flow which is in between. So this is basically related to the fundamental theorem of calculus. I will start with section A, which is basically the inverse problem of differentiation. I have a function, I want to know the function or the functions that give the given function as a derivative. Okay, so I have a function, I regard this as a derivative of something else. I want to find something else. I want to go back. It's a problem of it's an inverse problem. And it is, as all inverse problems, is in general more difficult to solve than direct problems. In other words, we have well-established set of rules to compute derivatives, and we can basically compute the derivatives of any function, but it's not easy in general to go backwards to compute integrals. Okay? And in some cases, there is no analytic solution to the computation of integrals. This is a very important point to understand. So, heuristic methods to compute integrals are very common. So, the heuristic approach, I mean, trying and see what happens, basically, is a fruitful approach for computing integrals. And also to solve the differential equation, which is the next step of our course. So basically, what is the reverse of differentiation? It's a very easy problem conceptually, nothing difficult to understand. Computing indefinite integrals means finding the antiderivatives of a function, or the primitives of a function. We know function f of x. We know this is the derivative of something else. We want to reconstruct the original function. Okay? A trivial example. Suppose that I have the function x squared. I know that the function x squared is the derivative of some function capital F. What is capital F? We know that capital F of x is equal to 1/3 x to the power of 3. If we take the derivative of this, the derivative is x squared, okay? So we know that this is one function having x squared as its derivative. Of course, this is not the only one. This is not the only one because any other function of the type 1/3 x to the power of 3 plus an arbitrary constant, any real number, has the same derivative. So the first insight is that when we go back, we don't have a unique function, it solves our problem. We have a family of functions, okay? Family of functions, but they have a property. There is take one of these functions, and all the other functions differ from this one by a constant, by just a constant, okay? So, and this is basically at the base of the definition of indefinite integral in the next slides. So this is just an introductory example. More generally, one can prove that, again, about our example, one can prove that any function having x squared as its derivative is prime. Okay, so not only we know that 1/3 x and this is the whole set of functions having x squared as its derivative. So the solution to our problem is a family of functions, and this is denoted in this way. I want to focus on this because it is a matter of notation, but also a matter of a conceptual matter. Okay, so this symbol is the symbol of indefinite integral. Okay. So we say the indefinite integral of x squared dx, this quantity, denotes the family of functions having x squared as their derivative. Okay? So this denotes a set of functions, a family of functions. When you write that the integral of x squared dx is equal to 1/3 x to the power of 3 plus a constant, we are just saying that the family of functions having x squared as its derivative is equal to this basic function, 1/3 x to the power of 3, plus any constant, okay? So it can be identified in this way. Take one of these functions having x squared as its derivative, add an arbitrary constant, and have reconstructed the whole set of functions that have x squared as its derivative. Is that clear? So this is a matter of notation, but also conceptual matter. This is called indefinite integral of f of x dx. We can take any primitive here, not only 1/3 x to the power of 3. We could take 1/3 x to the power of 3 minus 5 plus a constant, okay? It is exactly the same set, because C is an arbitrary real number. Of course, for convenience, we could write 1/3 x cubed plus 5 plus C. Plus 5 plus C is plus an arbitrary constant, again. So, when if we have a continuous function, f of x, when we write the integral of f of x dx, and you write that this integral is equal to capital F of f, capital F of x, sorry, plus c, we mean that the family of functions having f of x as their derivative is equal to any of the primitives of f of x plus an arbitrary constant. F of x, capital F of x, is a primitive of lowercase f. And this concept is expressed here. It is a primitive, it means that the derivative of capital F is equal to f of x. Okay? So this notation means that we are trying to find a set of all functions having f of x as their derivative. This set is given by any primitive plus an arbitrary constant. Writing this means that capital F is a primitive of lowercase f. That is, it has lowercase f of x as its derivative. This is called integral sign. F of x lowercase is called the integrand. It is the derivative. We have to reconstruct original function starting from a derivative. So lowercase f is the derivative from which we start. Dx, which has the same notation as the differential of x, indicates that x is the variable of integration. This is only y. In more sophisticated model, just a matter of notation here. But in other models, you may find expressions like this. Let me just write this for you, because you may find this notation, and it is just a very simple conceptual matter. You may find the integral between a and b, I don't know, of f of x y dy. Okay? So in this case, it is y the variable of integration, because I have a function of two variables here, okay? But when we have a function of one variable, it's clear what the variable of integration is, okay? But anyway, we have the same dx in the expression of the function, okay? So in principle, what I would like to say is that in principle, in the case of one variable, we don't need this. It's clear that the variable of integration is x, okay? But we anyway put this, also because of the origin of this integral, which is basically related to the computation of areas, okay? See later this. Okay, and C is called the constant of integration. So when we write that the derivative with respect to x of the integral of f of x dx is f of x, we are just writing something that follows directly from the definition of the integral, because the derivative and the integral are two different operators, okay, and that one is the inverse of the other, okay, inverse to one another. When we write that the integral of f prime of x dx is equal to f of x plus c, again, we are writing something that follows directly from the definition. Okay, so don't worry about this. This is similar to the exponential of the log of x, basically, okay, which is x, okay? Okay, so now we know that indefinite integral means finding the primitives or antiderivatives of a function. Given this, it's not difficult to try to write down a few simple rules of integration, okay? Any of these rules can be just checked. When we get the result, we compute the derivative of the result, and we obtain again the integrand, okay? Like in this case. Suppose that we solve this integral, then we compute the derivative with respect to x of our solution, we get again the integrand, okay? So basically, we know that when we take the derivative, don't look at this. Imagine a power function of x. When we take the derivative, we reduce the exponent by 1, basically. Okay? And the old exponent becomes a multiplicative coefficient. So if we have to compute the integral of a power function, x to the power of a, remark, this a must be different from -1, and the reason will become clear in a moment. Any real number, but not -1. We have to go backwards, okay, to reconstruct the function. So we have to increase the exponent by 1 and to divide by the exponent increased by 1. Why? There's no particular reason, it's intuitive, but if you want to be sure, just compute the derivative of this one. What is the derivative of this one? This is a constant, times a plus 1 times x to the power of a plus 1 minus 1. This becomes x to the power of a, and you can simplify a plus 1 with a plus 1, okay? So basically, here are a few examples, but suppose that we don't know the rule. If we don't know the rule, we can do something like this. Suppose that we want to compute the integral of what was the example? I don't want to make the same example. Okay. The integral of the square root of x dx. Okay? So this is the integral of x to the power of 1/2 dx. If this is the derivative of something else, this something else was something of the type x to the power of 3/2. Okay? Because when we take the derivative, we get x to the power of 1/2. So we'll reduce the exponent by 1. But this is not the end of the story, of course, because there is also a constant that comes into play here, okay? So basically, we have to apply the rule, increase the exponent by 1, divide by the same exponent increased by 1, add an arbitrary constant, and this is the result, okay? Why is that? Take the derivative. Plus c. Plus c becomes 0 in the derivative. 2/3 times 3/2 times x to the power of 3/2 minus 1. You can simplify here. And this is square root of x. Okay? So this is basically what we have to do. On another thing, suppose that we don't remember. We know that there is some constant that comes into play here, but we don't remember that we have to divide by the exponent increased by 1, okay? I could do something like this. I remember that the exponent here must be 3/2. And there is also some constant that comes into play here, okay? So there is some constant, a times x to the power of 3/2 plus c, okay? Now what is a? Compute the derivative. This is equal to a times 3/2 times square root of x, which is x to the power of 1/2. Now, this must be equal to the integral a to the power of a multiplied by 3 over 2 must be equal to 1, because the coefficient of the square root of x is 1 here, which means that a is equal to 2/3. This very simple, yet I would like to say this example trivial method to find a constant, because anyone can remember, of course, that we have to divide by the exponent increased by 1. But in some other cases, there are multiple constants that come into play here, okay? So if you remember the basic rule, but you don't remember how to introduce the constant in the integration rule, just use this method. Introduce an arbitrary multiplicative constant here in the solution, then determine the value of the constant by taking the derivative and by equating the constant that you have here with a constant that appears in the integral. Okay, so this is a very important rule. It's called basically it's used also to solve certain kinds of differential equations. It's called the method of determining the constants. Basically, it's based on the constants to be determined based on some condition. Okay? So this is quite important. I mean, in this example, it is quite trivial, but in general, it is not. It is very useful. Very useful. Okay, so here are other examples. What is the integral of 1 over the square root of x dx? This is x to the power of minus 1/2. Increase the exponent by 1, it becomes 1/2. Divided by 1/2 means multiply by 2, and this is the result. This is one other possible example of power integral of a power function of x. 1 over x squared means x to the power of minus 2, means x to the power of minus 1, because you have to increase the exponent by 1, and then divide by minus 1. So minus x to the power of minus 1 plus a constant. Minus 1 over x plus a constant. And so on and so forth. Here is another example. This is x to the power of 2/3, means x to the power of 5 over 3 divided by 5 over 3, means by 3 over 5, and this is the result. Okay? Now, why is this rule valid for any exponent, any real exponent a? And by the way, there are 2 more cases here to be seen in detail. This case can be regarded as particular cases of this rule.